What do floating trains, lossless power transfer, and the Large Hadron Collider all have in common, besides the fact that they're super cool? It all has to do with superconductors!
Bill Nye the Science Guy.
Bill Nye the Science Guy.
Bill Nye the Science Guy.
Science rules.
Bill Nye the Science Guy.
Inertia is a property of matter.
Bill Nye the Science Guy.
T minus 7 seconds.
Bill Nye the Science Guy.
So what is a superconductor? Is it a really great train operator? Nope. It's not the leader of an orchestra either. A superconductor is a material that, when cooled, takes on some really interesting properties. One of these properties is having zero electrical resistance, which is where they get their name from. Also, you can do some really cool things with them. One of the coolest visible properties of superconductors is known as the Meissner Effect. This is when you get a magnet to levitate above a superconductor, like so. When cooled below its critical temperature, a superconductor expels all magnetic fields. The magnetic field lines instead bend around the superconductor, acting as a force to hold both the magnet and the superconductor in place. One application of the Meissner effect that's already in use is for maglev trains. Maglev stands for magnetic levitation, and a maglev train literally floats above the tracks. They can reach speeds in excess of 350 miles per hour, and since maglev trains don't touch the ground, the only loss of energy they experience is due to air resistance. Recall that when a material starts superconducting, it expels all magnetic field lines, which in effect bend around the superconductor. If we line up a whole array of magnets, the superconductor bends their field lines as it approaches them. The superconductor is then free to move within a magnetic tunnel of its own creation.
Did you know that?
The fastest train in the world uses superconductors. Lead has superconductive properties at 7.9 degrees Kelvin. The first superconductive material discovered was solid mercury.
Now you know.
Liquid nitrogen is extremely cold, about 77 Kelvin. It's also a gas at room temperature. Make sure to wear gloves while working with it, and always work in a well-ventilated area. In the movie Iron Man, Tony Stark uses arc reactors to generate the enormous amounts of energy he needs to power his machines. Arc reactors seem inspired by superconductor technologies, but they've taken some liberties with the science. In real life, superconductors don't mean unlimited amounts of free energy, but if we were to make a generator out of superconducting materials, it would be over 99% efficient and take up half the space of a conventional generator. Superconductors come in two types. Their names are Type 1 superconductors and Type 2 superconductors. First, let's take a look at what goes on inside a Type 1 superconductor. Think of the material as a lattice of positively charged nuclei with a bunch of negatively charged electrons free to move around inside it. If the material is warm, every nucleus in the lattice is moving and jiggling about, and if an electron tries to pass through, it'll probably hit something. This is what we call resistance. But suppose we cool down the lattice, so the nuclei aren't moving around anymore. Now, any motion in the lattice is due to electrical interactions. When an electron passes between two positively charged nuclei in the lattice, they're attracted to it and come closer together. If another electron happens to be nearby, it's strongly attracted to these two close nuclei. If the timing is right, these two electrons sync up with each other and start following each other around the lattice. This is what we call a Cooper pair. If this starts happening all throughout the material, and we get a bunch of Cooper pairs vibrating the lattice in perfect harmony, this is when we get superconduction. You can picture a Cooper pair as one car following behind another. The front car makes it easier for the back car to follow by reducing the air drag felt by the second car. If we had a whole loop of these cars following one right after the other, they'd all be riding easy. While it's nice to think about Cooper pairs as a line of cars following each other, that's really just a classical description of a quantum effect. The real mechanism behind superconduction lies in the distinction between what we call fermions and bosons. 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 Now a fermion is a category of fundamental particle that encompasses just about everything you know. Neutrons, protons, electrons, and even neutrinos are all examples of fermions. One of the basic principles of quantum mechanics is that no two fermions can occupy the same place at the same time. This principle is part of what causes resistance when electrons flow through a material. When an electron, represented here by this cribbage piece, moves, it leaves a hole where it just was for a fraction of a second, because another electron can't occupy that space the very instant that it left. It takes a small amount of energy for another electron to fill that hole, and this is what causes resistance. When two fermions are locked together in an energy state, say a Cooper pair for example, they're considered a boson. A boson is another category of fundamental particle with drastically different properties from their fermion counterparts. Most notably, two bosons can actually occupy the same space. In fact, they want to. One boson comes down to the lowest energy level, then another boson comes and joins it, then it calls its friend. When a Cooper pair is moving through a material, it never leaves a hole behind it, because another Cooper pair is already instantaneously there. They never lose any energy trying to fill a hole, so they never experience any resistance. This is what makes Cooper pairs super cool.
Did you know that you can make a superconductor too? This is a yttrium-barium copper oxide superconductor. It is one of the most commonly made high-temperature superconductors. This is how you can make it. You'll need 12 grams of yttrium oxide, 40 grams of barium carbonate, and 24 grams of cupric oxide. You'll also need a mortar and pestle and a furnace capable of reaching 1,000 degrees C. Now we'll grind together all of our powder in the mortar and pestle. Once you have a consistent powder like this, fire it in a furnace for 18 hours at 950 degrees Celsius. After you take it out of the furnace, grind it up into a fine powder. Then, repeat these last two steps 2 times. Next, press your powder into a pellet. Once you have your pellet, fire it in a furnace with oxygen at 450 degrees Celsius for 10 hours. Now you've got your very own superconductor. Super cool!
I was in graduate school.